Well, hello everybody. I wanted to welcome you to the course with a sort of introductory video. And here you see a classic community college classroom. And it's the first day of class, let's suppose, and there's 30 of you sitting in these sparkling desks. And here's my welcome message here on the left whiteboard. And over here is the way I would run my traditional classes, a list of things to do, and we would check mark them as we progress so that there was a sense of driving towards the end of class. And something that you would have noticed if you were in this class is that at some point in time, a very propitious moment, I would tape up a piece of paper here and not tell you why I was doing that, but I do it at such a moment when most eyes were on me for maximum effect. And this is actually going to play into the magic trick that I'm going to do. It contains my prediction of some calculations. So let's zoom in on that whiteboard, and I wanted you to notice that the first thing on my list for the first day of class is the syllabus. And yes, I would actually read it out loud from cover to cover, and then have students sign it and hand that in, because it represents the covenant between us, the contract, the driving document that describes the course that we both have to adhere to. Now, being online, I've noticed students don't read it or they skim it, and I really want to impress upon you that you should read it. And in fact, I suggest reading it again in a couple of weeks, because you want to keep sharp on how the classes run. And you would be surprised at how many emails I get whose answers are actually in the syllabus. So yeah, my ulterior motive here is to encourage you to read this at least twice. We've already covered distribution. The inverse machine, maybe I'll make a video of that sometime. And the order of ops we've covered. All of these three things seg you quite naturally into the next part of the course, which is the movement towards word problems, which play big. And so I wanted to work the magic trick, which does that. It covers what we've had, and it covers where we're going. So I want you to imagine you're sitting in that room of 30 people, and I ask you to pick a number, any number. And I ask you to do that silently and internally. You're not to share it with anybody else. And theoretically, there's 30 of you. Very likely there could be 30 different choices. But let's keep this simple, because I'm going to ask you to do some mental calculations with that chosen number. So pick a number between 1 and 10. And what I next want you to do with that is I want you to add 9 to it. And of course that's going to generate a new number in your brain. And so having done that, I'll now ask you to multiply the result by 2. That is, would you please double it? Okay, I'm assuming you've got that. Next move is I want you to subtract 4 from whatever number is currently in your brain. Subtract 4. Keep in mind there's 30 people doing this, and they all probably began with different numbers. Next, after subtracting 4, I want you to take half of whatever's in your mind. In other words, divide it by 2. Okay, are you with me? We have one more move. I want you to subtract out the original number. So there you have 5 steps. And you all probably began with different numbers. There may have been some redundancy, but for the most part, lots of different numbers. And you went through these 5 steps. And what I would do is I would point to somebody in one corner of the classroom and ask them what number's in their brain. And then I would point to somebody else and ask what number's in their brain. And then I'd walk over here to this piece of paper and take it off and flip it over, and in bold you would see this. So if you have done these calculations correctly, everybody in the classroom should have ended up with 7. And what I want to do is get at the mathematics of that. So let's zero in again on the whiteboard. Let's create some space here. And what I'm going to do is drag in a expression. It's an expression because, well, it's not an equation. That's one way of putting it. It's an expression because it doesn't have any equal signs. And anything that comes at us this semester without equal signs is an expression. Most of the time we simply factor them or simplify them. And what I want to do is first explain the origin of this expression, and then I want to simplify it. So what I want to do is suggest that this expression is the manifestation of these 5 steps. Now x represents the number that I asked you to internalize, to think up, to pick a number. I don't know what it is. X is always the unknown, and so I label that number that's in your mind X. Next, I asked you to add 9 to it. And of course, I couldn't do this addition, but I could throw parentheses around it to show that you ended up with a single number after you added 9. Then I asked you to double it or multiply it by 2, and that's why this 2 is out front. The next step was to subtract 4. And this now represents a single number. I could throw parentheses around it. I didn't, but it does represent a single number if you change your perspective. And all algebra is a lot about changing perspective. So I said subtract 4 from it, and that's the result of that. The fourth step was to take half of whatever you had. And so I need to show everything up here being divided by 2 because now this thing represents a single number. And the last step was to subtract out the original number. And so this is the translation of this into algebra and operations and numbers. And the challenge for you will be to, in the bulletins, I'll ask you to actually begin with an expression and work back to the language. That will be one challenge. I have another challenge for you at the end of this video. Okay, what I want to do is show that this expression does in fact evaluate to 7. It simplifies to 7. That's the number everybody had in their brain at the end of the trick. So let me clear some space here and bring in the drawing program and do the math, do the simplification of that expression. So the order of operations say that we must do with what is within parentheses first, but I cannot do this addition. And it turns out there's an end around the order of operations. It's called distribution. It allows you to break into those parentheses with this multiplication. Notice x plus 9 is really a single number after you did the addition. And it's broken into 2 bits. And 2 must multiply both those bits. If it multiplies this whole number, it makes good sense that it multiplies both those bits. That's called distribution. And when we do that distribution, we end up with 2x plus 18. Now I'm just going to copy the rest of this and move on to the next step. And keep in mind what we want to know, does this evaluate to 7? Now at this point in time, I do have a multiplication here, and the order of ops would say to do this first, but I can't do that. We don't know what x is. And we have addition and subtraction here. Theoretically, according to the order of operations, we do them left to right. But again, I can't do this addition. And the question is, am I allowed to do this subtraction? And what I suggest you do is to prove to you it doesn't matter if you have all addition and all subtraction. It doesn't matter what order you do them in. I suggest you, just like I'm doing right here, just generate a random stream of additions and subtractions. And start here and then do this one. And in other words, you're not going to follow the order of operations. You're not going to do it from left to right. And then do it from left to right. And what you will discover is that the order of addition and subtraction doesn't matter so long as that's all you have is addition and subtraction. This is not true for multiplication and division. So you see the order of operations is a little more complicated, and getting good at algebra is realizing when you can violate the order of operations, which I am going to do right now by doing that subtraction. And this is what I get. At this point in time, I can't do this addition, I can't do this multiplication, but I can do this division. Everything up top is being divided by 2. Both terms. This is a single number divided into 2 bits. I can do that division, and this is a place where I see a lot of people break down. They don't realize I also have to divide this by 2. So there's actually 2 divisions by 2. In effect, the 2 is being distributed to both these terms. When I do this division, the 2's cancel, and I'm left with simply x. Very sweet indeed. When I reload and do this division, we have a plus 7. And so things are really simplifying here. And I think you could see that when you have a plus x and a minus x, they basically undo each other. They annihilate each other, and all we're left with 7. And in point of fact, everybody in the classroom, no matter the value they began with for x, should have ended up with 7 in their brains. The other thing I want to do is bring in an interesting video here. Probably America's most famous mathematician. This here is Arthur Benjamin. He teaches at Harvey Mudd College. He goes around the country giving lectures, and he was asked to make a math appreciation course for the Learning Company. And I have that course, and two of the programs are dedicated to algebra. This is the introductory course for algebra, and I'm going to play the first 2 minutes of it where he actually does a magic trick very similar to mine. I'll stop it before he solves it, and I'll ask you to write the expression and reduce it for a bulletin assignment. So I'm going to run the tape. It begins with a corny joke that I couldn't resist, just like Arthur Benjamin couldn't resist telling. You may like it and thank me for it. In which case I'll say right now you're welcome. So without further ado, here's Arthur Benjamin.
Welcome back. This time we'll talk about the joy of algebra. Now, I think the first time I experienced the joy of algebra was when my father asked me to solve the following problem. He said, okay, Art, I'm going to teach you algebra. 1q plus 1q is 2q. And 2q plus 3q is 5q. Now you tell me, what's 5q plus 5q? And I thought for a moment, and I said, 10q. And he said, you're welcome. Anyway, that was my first experience in experiencing the joy or the groan of algebra. In this lecture, we will learn to use algebra to explore mathematical magic tricks, how to do amazing mental calculations, how to solve linear equations, and even how to understand some of those dreaded word problems. The second time I experienced algebra was in trying to understand the following magic trick. Now, you have to all promise to do this right now, okay? I want you to think of a number between 1 and 10. All of you out there, think of a number between 1 and 10, okay? Double that number, all right? Now add 10 to whatever you're thinking, okay? Divide that by 2, and now subtract your original number. Concentrate on the digit, the number you're thinking of now. I'm getting the number 5. Is that what you got? Okay. So, let's see how this magic trick works. I think this is the best way to introduce algebra.